Good morning, everyone. Thank you for joining us for today's webinar. Today we're joined by Rob Huttemann and Tim Hirschenhofer to discuss best practices for managing airflow at the raised floor level. This is part 4 in a webinar series that takes a deeper dive into each of the 4 R's of airflow management. Our presenters today are Rob Huttemann and Tim Hirschenhofer. Rob is the Senior Vice President of Operations at Critical Environments Group. He has more than 30 years of industry experience in data centers and supporting infrastructure management. He specifically focuses on power, space, and storage, cooling, and overall facility best practices. Tim Hirschenhofer is the Senior Vice President of Operations at RLE Technologies. He has more than 15 years of data center efficiency experience with a focus on cooling, airflow, and data center monitoring. He's also a certified U.S. Department of Energy data center energy practitioner. Our agenda for today, we'll start with a brief recap of the 4 R's of airflow management. Then we'll really hone in on the role that raised floors play in aisle containment. We'll discuss managing bypass air at the floor level and how to match cooling capacity with your IT load. We'll look at the impact floor panels have in airflow management, best practices for managing airflow capacity and volume in a contained aisle. We have reserved time at the end of the presentation for any questions you may have. You're currently all muted and your cameras are off. Please submit your questions through the chat, which you can toggle on and off at the bottom of your viewing pane. If you prefer to submit your questions privately, you can send a private chat to RLE Technologies and we'll gather those questions as well. Out of respect for your time, we're limiting this webinar to an hour. So if we have allowed plenty of time at the end of the presentation for questions, but if we don't have time to respond to all of the questions, we'll reach out directly to you after the webinar and personally review your questions. And with that, I'll hand it over to Rob.
Thanks, Jenny, and good morning, everybody. We've been referring to the 4 R's of airflow management throughout our webinar series as a methodology for identifying and implementing changes to optimize a data center's cooling infrastructure and realize energy savings. We use the 4 R's to break down functional elements of the data center that can play a role in the overall optimization. So the 4 R's are the rack, the row, the room, and today our feature is the raised floor. So let's do a quick recap of the previous 3 R's. At the rack level, we emphasize the importance of taking care of the low-hanging fruit or aspects of airflow management that provide high value at a generally lower cost. We provided education about bypass airflow and the various ways it can negatively affect the cooling infrastructure and how by implementing best practices at the rack level, you can help essentially set the stage for airflow management improvements at the other levels. Rack airflow management deals primarily with sealing unused U spaces and cable openings in the rack and any open spaces in between racks. I'm hearing a keyboard chatter, so maybe that could be muted, please. So I want to elaborate a little bit. So at the rack level, for those of you who weren't on that presentation, so really the unused U spaces in the rack, that's a simple one. Everybody gets the term blanking panels. There's a lot on the market from a lot of different manufacturers. It is a best practice. It is low cost and high value. One thing we see more and more today than we have seen in the past is, so you've got taller racks like in excess of 50U, you got wider racks, 28, 30, 32 inches wide, and most of those have 19-inch rack mount down the center. So you got these gaps between your rack mount rails, the sides of the cabinet, and they extend from the bottom of the cabinet all the way to the top. So if you're 52U, you got like 96 inches times 4 inches wide of an open gap that they use for a lot of high density cabling, typically. Those need to be blanked off as well so that hot exhaust air from the rear of your racks doesn't wrap back around through those big gaps. And brush strips are most commonly used there because you can reach your hand through it if you need to, penetrate that with a cable and still block the opening, etc. So just pay attention to that as well, not just looking at the blanking panels in between the U spaces, but those vertical gaps. So when we move to the row level, we're looking at ways to best separate what could be significant levels of supply and exhaust air mixing that can occur in a hot or a cold aisle. So this is where we introduce the use of aisle end doors, overhead baffles, and capped aisles. So, you know, airflow is kind of unique in that you can kind of feel it temperature wise, and you can feel it moving like, you know, a fan or a breeze, but you can't see it. And even if you've done hot and cold aisles and you've got your racks orientated properly, there's a significant amount of wraparound that comes from the hot aisle into the cold aisle at the aisle ends. And there can also be a significant amount of wraparound from the hot aisle over the tops of the racks and into the cold aisle. And that's why we talk about a best practice for implementing aisle end doors and potentially capping or using an angled baffle for cold aisle containment, or panels that go directly up, or chimneys in hot aisle containment. So those were the best practices around row airflow management. Our last webinar was on room level airflow management, and we stressed that this is really where the rubber hits the road, and that this is where the real cooling optimization takes place and where energy savings can be realized. All the best practices you implemented to separate the supply and exhaust air at the other levels are now just an expense, right? You paid to do all of these things, but if you ignore making the changes to your infrastructure to truly take advantage of your airflow management initiative, you're falling short. So the onus goes back on you, the owner or the data center manager, to tweak your set points on your crack or craw units, to potentially put units in standby and pick up some redundancy, raising chilled water temperatures perhaps. All of those kind of things that you do as the owner after you've done the best practices implementation, that's where you're going to realize the savings. So that brings us to today's topic, is on the raised floor level and its associated best practices in the overall scheme of the 4 Rs. So while a bit out of sequence due to scheduling changes we had to make due to the pandemic, it's an important step in the overall process and not to be overlooked. Floor level airflow management is basically done at the same time or right after you start implementing the rack level best practices, and we break it down into 2 key aspects that we'll dig a little deeper as we move through the presentation. The first is sealing the openings in the raised floor. Pretty simple, but we'll go through those details. And the second, really a 3-parter here, managing the type, the location, and the quantity of the perforated tiles that deliver the supply air. So now I'm going to hand it off to Tim. He'll talk about the raised floor, how it's built, and its role in aisle containment.
Thank you, Rob. Before we get into the role of a raised floor in aisle containment, I think it's important to quickly review how a raised floor is built. Raised floors are comprised of pedestals, usually a flat square piece of metal attached to the top of stanchions that connect to stringers on 4 sides. Stanchions, which are the vertical supports between the subfloor and the pedestals. The stringers, which are the horizontal cross members between the pedestals. And finally, the panels that sit in or on top of the stringers and pedestals. Pedestal heads can typically be leveled by raising or lowering the pedestal head in the stanchion with a large screw assembly. Ensuring that the floor is level is not only critical to safety and the floor structural integrity, but it also prevents excess cooling loss through gaps in the panels and stringers and the pedestals. The role of the raised floor in the data center is basically to provide a pressurized plenum of cooling air, and through the use of airflow panels, focus that cooling air where it's needed while supporting the weight of the IT cabinets and other equipment. It can also be used as a space for running electrical, communication, and mechanical services. Plenum depth can vary from space to space, but most are between 6 and 48 inches deep. The role of the raised floor when using aisle containment remains basically the same, except that it becomes easier to match the cooling and IT loads due to reduced mixing of hot and cold air within the room. Properly installed containment helps ensure that the cold air supply and the warm air return remain separated, increasing cooling efficiency. Part of properly installing containment really includes managing bypass airflow at the floor level. And as Rob kind of mentioned before, this is fairly straightforward. The floor should be level, so the panels fit tightly together and flat against the stringers and pedestals. And here's where the first of the two key aspects discussed earlier come into play: sealing any open cutouts. We typically see floor cutouts around piping, electrical conduit, and under server racks. Sometimes you'll find very large cutouts around floor standing PDUs, for example, to enable the large quantity of whips that can come out of the bottom of the PDU. The pictures in this slide show some examples of these cutouts. Any cutouts in the floor panels should be filled with grommets or flame-rated foam to prevent cold air from leaking into the room in undesired places, and gaps between racks and floor panels should also be filled. And this leads us to the second key aspect mentioned earlier: managing the type, quantity, and location of perforated panels.
So Tim, thanks. I just wanted to add a couple things here. So sometimes covering up tile cutouts under racks that are already in place and have cables coming in, maybe easier said than done. So I see there's a fair amount of racks out there that the bottom of the rack is open, right? You just have the perimeter of the frame and maybe some brackets for the levelers and casters. And it may be easy to access that open cutout where you may have power and data cables coming out. And it's easy to address it when you can see it. If the rack's got a solid base, you may have to take some other types of initiatives to kind of plug that. And we talked about some products in the earlier presentations that blank off like from the bottom of the rack to the floor. Or, if you can move the rack a little bit, easier said than done, I know, maybe you can get in there and fill that hole. But that it's important and not to overlook it. The rest of these, like the pictures show, are in the open, so to speak, right? They're usually around the perimeter of the room where you've got piping, electrical conduit, mechanical piping, fire suppression, those types of things coming out. And it's usually a cutout, where the floor hits the wall. Those are the things that you see in the examples of the pictures here, and it's important to seal those as a best practice as well. Definitely don't overlook those.
Yeah, good points, Rob. We're going to talk now a little bit about airflow panels and managing bypass air. Airflow panels should be managed so that they're in the right places, providing the right amount of airflow. And we'll talk a little bit more about how to determine this in upcoming slides. Dampers should also be used on airflow panels planned for future growth or where IT loads are lower now but may change over time. And you can see by the pictures in this slide that there are many different types of perforated panels. So it's important to know some of the differences between them when considering their use in your containment projects. The main difference between panels is the percent of free airflow that the panels will provide for, because it's through these panels that the supply air enters the aisle and from which you're trying to match or exceed the IT load in that particular contained aisle. In the past, when server rack densities were lower, most data centers just use the kind of standard 25% perforated panel, and that could typically keep up with rack densities in the 2 to maybe 4 kilowatt range. With today's higher density racks, it's now much more common to see high performance airflow panels used, like the two shown here in the center of this slide.
Thanks, Tim. So matching the cooling capacity with IT load. We recently published an article in Mission Critical where we quoted Ken Brill, one of the founders of the Uptime Institute, who said, when it comes to data center cooling, it's as simple as power in, heat out, always. So in other words, every kilowatt of power consumed in the computer room becomes a kilowatt of heat that needs to be removed from the computer room and ultimately from the building. So this includes all power conversion and distribution losses, as well as every kilowatt of electricity consumed by the IT equipment. So this is why it's critically important to match or exceed the cooling capacity to the IT load, and it's the role of the raised floor and the correct type, quantity, and location of the perforated tiles to distribute the necessary cooling capacity. So determining your opportunity for optimization. So I'm going to back up for a minute, go through some of the important metrics and conversions we use in identifying capacities. This has been addressed on some of the previous presentations as well, but we use watts as the common metric for both power and cooling, so that 1 watt of cooling needs to match or exceed each kilowatt of IT load or heat that needs to be removed. So looking more closely at this slide, that first bullet is really to get your arms around your overall cooling capacity in kilowatts. So there is a conversion factor that converts tons to kilowatts. It's 3.52. So if you add up the cooling capacity in tons, if you have 5 20-ton AC units and you multiply that by 3.52, that's 100 tons. So that would be 352 kilowatts of cooling capacity, roughly, that you have available to you. So that's half the equation, right? The next bullet says, about capturing your IT load. Bunch of different ways to go about doing it. I have one here, reading the output capacity of your UPS. That can be done on some, at the UPS user interfaces, through monitoring software that comes with your UPS, and sometimes even from any type of monitoring associated with an RPP, if you're using those to distribute power into your aisles, as well as from floor standing PDUs. Even more granularly, there are the power strips in the backs of the racks that oftentimes have current monitoring or even power consumption right there on the strip itself, or through a monitoring interface. And we'll talk a little bit more about monitoring later in the presentation. But once you've got those two pieces, you can make kind of some quick high-level determinations when you're comparing your total kilowatts of cooling against what you feel is your IT load in kilowatts. And ideally, that ratio should be about 1.2, giving some level of cooling redundancy. And any ratios higher than that will indicate an opportunity for optimization. So even today, and this has been going on for a while, right? We've all heard this, but even today, we still see data centers that are 2 times, 3 times, or even more overcooled. So there's still a big opportunity, and you can self-assess your own data center by doing those kind of 2 high-level comparisons. So now I'm going to hand it back off to Tim, who's going to go through some specifics about the floor panels and their role in proper airflow management.
Thank you, Rob. The role of airflow panels in a raised floor environment is really to provide enough cooling air in front of a given server rack or racks to ensure that servers remain at safe operating temperatures, ideally without overcooling the space. This CFD, or computational fluid dynamics model, shows a limited airflow velocity with a standard 25% perforated panel. As we look at the 3 CFD images, it's important to note that all of the CFD modeling parameters were exactly the same for each panel modeled, and you'll see that there are wildly different results. This slide, along with the next two, really helps illustrate why airflow panel selection is important. This airflow panel provides much higher airflow velocity, but the design of the panel directs air straight upward, allowing most of the airflow to bypass the server rack. And I know this is true for Rob too. In both of our careers, we've been in hundreds of data centers across the country and even around the world, and working with customers to help improve cooling and efficiency. And the scenario shown here by the model on the left here in this slide, where the conventional wisdom is to use a high flow airflow panel and assume that proper cooling is taking place, when the reality is quite different, is a lot more common than you might think. Finally, this airflow panel directs more air at the rack, reducing bypass airflow and providing much more effective cooling. So it's pretty easy to see by these 3 CFD models that not all airflow panels are created equally or provide the same amount of cooling or directed airflow. Now I'm going to hand it back to Rob, who's going to identify some of the best practices for managing airflow capacity in a contained aisle.
Thank you, Tim. we're now going to take a look at 6 of the best practices for managing airflow capacity in the contained aisle at the floor level. So we're going to go through plugging the holes, dealing with obstructions under the raised floor, the importance of leveling and weight ratings on the floor tiles, a little bit more detail on the capacity and flow calculations and the associated panel requirements. And then we're going to get, as I mentioned earlier, a little bit more into some of the monitoring options. So the first best practice is plugging the holes. Tim mentioned this earlier, and I chimed in a little bit when we had the pictures of the holes around the perimeter of the room and under the rack. So one of the easiest and most cost-effective best practices to implement in the data center is to plug all the holes in the data center environment. We all know this, yet many of these solutions are only partially implemented or never maintained over time. So using blanking panels and racks, grommets and/or fire retardant foam and floor cutouts and in between the racks and floor, and sometimes baffling under the floor, can still contribute to more efficient cooling. So this becomes even more critical when using aisle containment. Because if air can escape the contained aisle through these types of openings, you're limiting the effectiveness of the containment and decreasing your cooling efficiency. These measures are cost-effective and easy to implement in existing or new data centers. So let's kind of take a look at what we've got here on the slide, right? So floor grommets, so holes in the floor that have cables coming up through them. So you've got existing holes that have cables coming up through. So how do you plug that? Because you need to kind of clamp around the cables. So you've got 2 kind of typical flavors, like rectangular cutouts or circular. And you can see from the slide here, if you've got existing cables coming up, you can have a grommet that can be separated. So you can clamshell the cables, whether that's a rectangular opening or a circular opening. And if you've got a new cutout, if you're provisioning new racks, if you're building out, you want to make sure that the cutouts you're going to do match the requirement of the grommet that you're going to put in its place. But you can put in a grommet that's already kind of comprised. It doesn't need to be clamshelled. It can be snapped together or an integral design so that it goes right in the floor, and then you can bring your new cables up through it. When you've got, and now at the bottom picture, right? So not as elegant sometimes as the grommets, but the fire retardant foam plays a major role, right? So you've got odd shape openings. You saw it in the earlier slide with those like electrical wires coming up or the piping coming up. You've got some odd shaped cutouts, and usually not a lot of thought gets put in, hey, I've got a really big cutout. I can, it's easy for me to get this around the pipes, and you've got more open area than you did with the pipes coming up. So you can use this foam product, and it usually comes kind of diced in 2 dimensions, right? So you can break apart chunks. These things usually ship like a floor tile, 2 by 2, 2 foot by 2 foot dimensions, about 2 inches thick, and you can break it apart so that you can kind of wedge in the exact amount of foam you need for the type of opening you want to close. Now I'm going to hand it back to Tim, who'll talk about obstructions and clutter in the data center floor.
Thanks, Rob. Anyone who's been in a legacy data center or who may have had the unfortunate case of inheriting an old legacy data center is probably familiar with this, but we're going to talk about dealing with obstructions and clutter under the floor. Things like chilled water pipes, cable trays, and shallow floors and legacy cabling can all contribute to reduced airflow through airflow panels. And although not always possible to retrofit in existing spaces, building a deeper plenum can help mitigate some of these issues. Also, limiting chilled water piping to the perimeter of the room and regular cleaning and removal of legacy cabling can all help in maintaining proper cooling throughout the data center. I actually worked with a data center a few years ago in the Minneapolis area that was originally designed with a relatively shallow floor. I think it was about 14 inches deep. And it just had a poor design. It had large chilled water pipes running directly in front of every cooling unit in the room. So this obviously restricted airflow and caused a lot of cooling problems for this particular customer. And the problem was so severe and impeded the cooling ability of the crack unit so much that the customer actually decided to move the chilled water pipes from under the floor to overhead around the perimeter of the room. And as you can imagine, in a live data center, this was an extremely large and expensive undertaking. But the cooling improvements gained from the project paid for itself in both the ability to increase total cooling capacity and therefore increase IT densities in that same space. And when taking all of that into consideration, the payback for the project was projected to be less than 2 years. So even in existing legacy spaces, steps like this can be taken with relatively short project paybacks.
Yeah, thanks, Tim. I'd actually like to, can you go back to that slide, please? So I'd like to kind of chime in a little bit too. So we see a lot, unfortunately, of what's on the left and a little bit in the center. And most people we talk to say that that's what they inherited from the previous guy or gal. But nonetheless, it's a big problem, especially in a shallow raised floor, because if that is your means of delivering cold air to your racks, and you've got a raised floor that looks like the pictures, you got some big problems. A best practice, which wasn't one of the 6 listed, is you got to keep the clutter down under the raised floor. There should be some methodology in kind of your model of how you operate to get those unused cables that you keep piling the new stuff on top of out of the floor. You know, I've been in this for a long time, and I actually saw when we went from mainframe to distributed back in the early 90s, people just piling the new Cat5 cables on top of the old mainframe cables. So that's, you know, it started then. But this is not good. And you should have some kind of policy or periodic scheduling of downtime where you're doing upgrades, et cetera, to kind of weed out the stranded cables that are under your raised floor. Or else you are going to have issues with, even if you have enough cooling capacity, you do the 3.52 times the number of tons, and you say, yep, I'm right in range, and you can't get it to where it's needed because of this. So you've got another set of problems on your hands. So a best practice is to kind of pull the unused cables and get rid of them so that anything in that raised floor is actually active and required. The other thing is a lot of people are doing it overhead now. You know, it might be power under the raised floor, data overhead, you know, fiber troughs for fiber, and then a ladder rack for copper. That gets rid of a lot of this, but you'll be shooting yourself in the foot if you just put the floor tile down on top and say, I can't see it, therefore it doesn't exist.
Hey, good points, Rob. I'm going to talk a little bit now about leveling and weight load considerations. And I think this is something that's often overlooked when it comes to your data center flooring. Most solid and airflow data center panels are identified by their concentrated load ratings. So, for example, when you hear a panel referred to as a 1,250 pound panel, that panel has a concentrated load rating of 1,250 pounds. A fully loaded 42U rack can weigh over 1,600 pounds. So as racks become taller and even more densely loaded, data center panel weight ratings become increasingly important. Standard options available on the market range from 1,000 pound to 5,000 pound rated panels. And again, I'm referring to concentrated load ratings with those numbers. As you can see from this slide, there are many other load tests that raised floor panels are tested for. However, concentrated and rolling load tests are most commonly referred to when discussing data center flooring's weight or load ratings. It's also important to note the rolling load ratings of the panels in your data center, because that's typically how things are moved in and out of the data center. And keep in mind that rolling load ratings are typically less than concentrated load ratings for the same panel. And I've worked with several customers in the last couple of years to replace floor panels that have been damaged and deformed from loads that have exceeded the manufacturer's weight rating specifications. And we had one customer last year who actually had 2 racks fall through their raised floor. Luckily, no one was hurt, but as you can imagine, this prompted a swift replacement of all flooring panels in the data center with new panels at a higher load rating. And this is something we're seeing increasingly happen, where older floors are being tasked to hold more and more weight, more and more or higher and higher rolling loads. And they were never intended to take that amount of weight or stress. And again, leveling plays an important part in these weight ratings, as all testing done on these panels is done on level panels. So the load ratings assume that the panel is installed properly and is level, and an unlevel panel or uneven floor is not necessarily going to be able to support the same weight as its load rating indicates. When it comes to airflow panels, it's also important to understand that not all airflow panels will fit in all flooring systems. There are different manufacturers out there, and they tend to make their airflow panels fit in their flooring systems without a lot of consideration for other manufacturers' flooring systems. The images in this slide show the underside corner of two airflow panels. The panel on the left will fit into just about any flooring system because it's equipped with adjustable leveling bars and set screws, whereas the panel on the right will only fit into a specific manufacturer's flooring systems. The panel on the left can also be adjusted to match the level of the existing floor, even if there are small differences between the four pedestal heads supporting the panel. In that same scenario, the panel on the right will end up rocking or wobbling, which again potentially degrades its weight rating.
Thank you, Tim. So we'll talk a little bit more about capacity and flow calculations. So understanding the IT load you need to cool and being able to match it or preferably exceed it with your cooling capacity has now been mentioned in each of our webinars about aisle containment, and you just heard it from me a few minutes ago, so it's that important. So in the context of the overall load and associated cooling capacity, we showed how you can use watts as the common denominator and how to convert tons of cooling into watts so you can compare the capacity using the same metric, right? Tons times 3.52 equals the number of kilowatts of cooling. But at the contained aisle level, however, especially with cold aisle containment with a pressurized raised floor, unless you have a tool that uses sophisticated mass airflow sensors to show watts of cooling at the tile level, it's important to understand the airflow ratings and the requirements of your equipment in the contained aisle and be able to match and exceed those flow ratings with what you deliver into the contained aisle through the perf tiles. So a bolometer, which is what you see kind of in the middle there, or a flow hood, which is what we usually refer to it as, is a good tool to assist with measuring CFM output at the perf tile level, assuming it's equally calibrated. So you're like, okay, I can get CFM now, but you told me we got to use watts. So how do you do that? So at the contained aisle level, I'll explain a little caveat around this at the end, but at the contained aisle level, you can use 156 to 160 cubic feet per minute CFM per kilowatt of IT load as a rough rule of thumb. So here's the caveat. Just like with anything, there are factors that affect that plus or minus, right? So 156 to 160 assumes you're at sea level, you got about 65% relative humidity and maybe a 20-degree delta T, right? So you can get your IT load at the rack level via smart power strips, like I said, or with the RPP, or with a floor standing PDU, or at the row level using intelligent PDUs, and multiply that total by 156 to get the total number of CFM required for distribution into the cold aisle. You would then refer to your floor tile manufacturer's specifications and ratings for the perf tiles to make sure you're selecting the type, the quantity, and the right tiles that can deliver that amount of CFM. So now you're going to come back to this kind of chart. You got a spec sheet on perf tiles from whoever you're looking at, and usually you've got some performance metrics and graphs on that spec sheet that are going to help you make this decision. So Tim, if you don't mind, if you could kind of go through a little bit of what the graph shows and how an end user might use it to make these decisions.
Sure. So this is pretty typical of pretty much any airflow manufacturer's chart. And basically what it shows, and what's important to understand in looking at this, is knowing what your plenum pressure is. If you look across the bottom of this chart, you'll see different incremental measurements of plenum pressure in inches of water going from 0.01 inches all the way up to 0.1. And basically going on the left side, going up the chart, you've got your corresponding CFM. So this chart is showing a comparison between two panels represented by the red and blue lines. And for each incremental measurement of plenum pressure, you can see for each panel the expected CFM you can get out of each of those panels. In this case, the panel represented by the red line outperforms the panel represented by the blue line just slightly, but that performance increases as pressure increases. So if you know your plenum pressure, if you're monitoring your plenum pressure, you can definitely look at one of these charts and relatively quickly understand how many panels you'll need to satisfy the cooling load in a given aisle. So as we just discussed, looking at a floor manufacturer's airflow ratings really allows you to calculate what type and how many panels are required to cool a given rack or row of IT equipment, and matching the airflow panels to the IT loads in a contained aisle becomes even more straightforward, because theoretically, almost all of that cold air supplied into a contained aisle will be utilized by passing through servers with very little waste or bypass airflow. Using these calculations as a starting point is important. And I've been in many data centers where way too many airflow panels have been placed in cold aisles when compared to the actual IT load, kind of like the picture there on the right side of the slide. The assumption being that more is better. And overcooling a cold aisle is definitely inefficient and is also detrimental to preserving floor pressure, which in turn requires more fan power usage from the cooling units and therefore higher cooling costs. Taking all of that into consideration, it also must be remembered that real world conditions in data centers can affect the amount of air flowing through a given airflow panel. Pressure is not necessarily evenly distributed throughout the floor plenum. Low pressure areas in the floor, or things that we've previously discussed like underfloor cable dams and chilled water pipes, can reduce the amount of airflow in certain areas within a data center room, thereby reducing the effectiveness of airflow panels in those affected locations. So cooling load calculations typically don't account for these factors, which can result in a correctly calculated panel count for a given area, but still come up short in quote unquote real world cooling effectiveness.
Thank you, Tim. So this brings us to our last best practices, monitoring. So an effective way to know if you're providing enough cooling for a given rack or row is to monitor temperatures. Temperature monitoring ensures that low airflow areas, and therefore typically higher temperatures, are identified and can be addressed. So in addition to temperature monitoring, differential air pressure between the floor plenum and the data center room, and or between a contained aisle and the rest of the room, air velocity and humidity can provide important feedback about the state of the cooling and airflow in a given space. So armed with monitoring knowledge, it's easy to make adjustments to airflow panel numbers and locations to address these areas. So looking at this slide, right, you've got your typical data center hot and cold aisles sitting on top of a raised floor with a airflow plenum underneath. And you got some call outs for some different types of monitoring as examples. So under the raised floor, you heard Tim talk about the differential pressure. And this is where you'd have those sensors. You'd also have air velocity sensors available that can be positioned under the raised floor. And there's also other types, right? There's smoke detectors. If there's fire suppression in the raised floor, there's leak detection down there as well. And above the raised floor and at the rack levels is where you typically see your temperature and either a temp/humidity sensor, either a temperature standalone or temperature humidity combined. And then somewhere in this whole scheme, you've got what we refer to here as the monitoring manager. It's usually a network appliance. It can be a standalone with its own user interface that you manage your monitoring network, It can be on its own network, and we'll talk a little bit more on the subsequent slide about, whether this technology is something that you're going to run wires to all these sensors or do some wireless. So we're going to go through that in a little bit more detail. Next slide, please. So you just heard, those examples of solutions available in the data center, but there are a lot of factors to be considered when choosing a monitoring platform. So this slide shows an example of one of those important considerations for monitoring solutions today, and we run into this a lot more frequently, is really deciding between using a wired or wireless solution. So I'm going to go through a little bit on the content of this slide, but wireless is initially, when it was introduced, a lot of pushback around security, a lot of pushback because you might have information that could leave the data center. What if someone hacks it? Can they get in and do things to my network and connect to things I don't want them to? And I think a lot of that has been kind of addressed by the manufacturers pretty well, where those initial fears are overcome, and we're seeing a lot more adoption of wireless monitoring in data centers today than we ever have before. But that said, there are considerations you need to get into, like the line of sight distance. Am I going to be sending wireless signals that have to penetrate walls or other obstructions, and can I achieve this? Most wireless sensors have some type of battery that powers them, whether they're velcroed onto the front of the rack or zip tied onto the front of the rack or on a pedestal under the raised floor. They got a battery that allows them to operate. And the amount of times those sensors are pulled by the appliance or your monitoring brain, the more that battery gets used. So you want to just be aware of the battery life. Most monitoring solutions today use RF frequencies that don't interfere with anything else going on in the data center. There are frequencies allowed in the United States that are typically used by the manufacturers, and different frequencies in other parts of the world. But the RF doesn't interfere with anything. A lot of the transmissions from the sensors themselves are just that. It's just temperature data, and most times that data is encrypted. So you can't even hack it and understand what you're looking at. And it's one way. It's one way out from the sensor and not back to the sensor. So you want to also look at how you're going to use the system, right? Am I going to integrate these monitoring sensors with a larger BMS or DSIM tool that I spend a lot of money on? So you want to make sure that if that's the case, that your sensors can output information into common protocols that you're able to integrate and input, like SNMP or Modbus or BACnet. And the diversity of the sensors and options that can be used with the system. So scalability, right? My data center is growing. Is this guy going to be around as I scale? Can I add more sensors, and can his appliance accommodate more? Am I going to have to upgrade that at some point in time? So these are just some of the considerations you might go through when selecting a wireless versus kind of wired. And we didn't talk a lot about the wired, but I think it's pretty obvious. The sensors are tethered back to that main controller. So you've got a lot of wires you got to deal with. And if you're under the raised floor, it's just adding to the count that you already have down there. So this now takes us to the conclusion of our presentation today. But before we get into reviewing these key takeaways, I want to take some time to thank you all for attending today's presentation. An additional thanks to those of you who attended our previous 3 presentations or any of the previous 3 in this series. I also want to thank our partners at CPI and Upsite who supported us on the previous presentations, and from which some of their content made its way into today's presentation. And certainly to RLE Technologies for their support with today's presentation. Lastly, I hope you and your families and coworkers remain safe and healthy through these trying times. So now for the key takeaways from today's presentation, and then we'll move into the Q&A. We talked about kind of raised floor airflow management as the kind of the phrase for managing airflow through the horizontal plane of the raised floor. And the two key aspects to raised floor airflow management: ceiling only openings in the raised floor other than the supply panels, and then the three-part, for the second one, of managing the type, the location, and the number of the supply panels. And Tim did a good job kind of explaining the differences there and kind of what things you need to consider. We talked about the raised floor being, that's what ensures the cooling capacity in the room and being able to properly deliver it to the cold aisle. So you got to get that right. And then, we went into 6 best practices for floor level airflow management and kind of listed 4 of them here. Managing the bypass airflow by plugging the holes. That's consistent from the rack into the floor, and that's why we talked about that those 2 aspects of the 4 R's usually kind of go hand in hand or done with one another, or one right after the other. Understanding the negative effects of underfloor obstructions and clutter, and the best practice to kind of deal with that and manage. I mean, you do virtualization or put applications in the cloud, and you hear a lot of people talk about stranded capacity in the racks. These are servers or other devices that are on, consuming power and not doing anything. And you pull those out, right? And you get rid of it, and you have available capacity you just reclaimed. But not a lot of talk about the same thing going on under the floor. So if you can do it, I'd get started. It's going to do nothing but help you longer term. Tim did a good job of talking about how to select the proper perf tiles, and I just kind of concluded on the different types of monitoring that might go hand in hand with the overall management of airflow in the data center. So with that, I think we'll conclude the key takeaways and move on to the questions. Jenny?
Yeah, you guys have some great questions lined up, so let's dig into those. There are definitely some questions about monitoring. So let's start with this one because it's got a couple people interested in it. What is the recommended number and location for rack-mounted sensors, both height and along the rack row?
All right, so I'll try taking this one. There are, I wouldn't say conflicting opinions on this, but there are some. So every site's a little bit different. If you look at ASHRAE and kind of what they're talking about is, they'll say things along the lines of 3 sensors on the temperature sensors equally placed on the bottom, middle, front of the rack, and 1 on the rear. It's a lot of sensors on racks. We've seen effective rack level temperature monitoring happen on different quantities other than every rack. So maybe every other rack or every 3rd rack, or certainly on the racks that are given or have the highest kind of heat loads associated with them. Those are the ones that are usually some of the root causes of cooling issues, or kind of low-hanging fruit if you're doing temperature monitoring to say, hey, I've got an issue here. There are some vendors that'll show effective temperature monitoring at 2 sensors on the front and 1 on the rear. So it kind of depends. We talked a little bit on one of the earlier presentations about selecting a vendor partner who is very knowledgeable about their technology or what they're providing to you, and not just somewhere where you can buy product, because those folks will know. You can get a lot more granular too. I mean, there's manufacturers that'll sell wired sensors that have 3 sensors kind of all strung together, so that you can kind of connect all 3 at once on the front of the rack. That's nice if it's a wired technology, then you don't have like 3 wires, 1 coming from each sensor. So there are different manufacturers options out there. There's a lot for both wired and wireless. The more you have, the more granular you can get, but sometimes it's a point of diminishing return based on kind of how the loads are dispersed in the racks. Hopefully that helped answer it.
Yeah, Robin, I'd just like to piggyback on that a little bit. I mean, I don't, I mean, based on our customer interaction, we have not seen, I don't think, one customer deploy sensors in the same fashion from customer to customer. Some will recommend or install sensors at the 5-foot level on every third rack. Some will just go to the highest point of equipment in a rack, whether that's 3 feet or 6 feet. And that's where they want the sensor, because the thought is if cold air gets to that point, if they're monitoring at the highest point in the rack where there's equipment, then they know they're safe. So it's really all over the board.
Yeah, and you raise a good point at the top of the rack, because, you know, with cold aisle containment, you know, that's usually your highest inlet temperature is at the top of the rack. I think that makes sense to everybody. And we have customers that will put aisle end doors, won't do anything to cap the aisle or baffle any of the cold air to keep it in the aisle, and they use that top of rack sensor as part of feedback to like their VFDs, so they call it the bathtub effect. So they can modulate the amount of cold air they're providing to that cold aisle. When they kind of dial in the temperature they want at the top of the rack and get there, they kind of back off with the VFDs, and they use it in part of their controls scheme to effectively, you know, cool their aisle safely and efficiently, and just refer to that as the bathtub effect.
All right, guys, I'm going to move you on to the next question. In a fully cold aisle containment closed on top, would you consider using low air pressure monitor inside the aisle to avoid overpressurizing the aisle?
Yeah. I've seen, you know, just like Tim was talking about his experience in Minneapolis with the racks falling through the floor. I mean, we've seen customers blow the roof off, literally, with overpressurization in the contained aisle with a capped roof. Like, we've seen people blow the roof off a contained aisle. We've seen people pop ceiling tiles because of pressure. Honestly, we've actually witnessed it. So monitoring that kind of pressure that you're delivering, and you always get a little bit of leakage, you know, when you don't want to like a hermetically sealed cold aisle, because that could be kind of problematic as well. So having a little bit of kind of leakage, you know, maybe at the top of the doors or where the roof panels hit the racks, et cetera, it's not necessarily a bad thing, but monitoring that and being aware of it is would definitely be something that wouldn't be money that would not be well spent.
And there's a lot of good options, Rob. There's some that can fit in the floor to tell you the differential air pressure between the floor and the cold aisle, and then others that can be kind of rack mounted to give you an idea of the pressure between the front and the back of the rack. There's just a lot of options for doing that. It's relatively inexpensive, and as you just mentioned, it's probably worth the money to do that.
Guys, there's a question that ties right into this. Is there a common or best value for differential air pressure?
You want to take that, Tim?
I don't think there's a best value. I mean, you know, the issue is every data center is different. I have never been in two that are exactly the same. I know the target is to lower your differential air pressure or your plenum pressure, because the lower pressure you can safely operate at, the lower fan speed you can run on your crack units, and the more efficient you can be. But as we mentioned, you know, if you've got a legacy site with issues in the floor with some of those things we discussed, cable dams and things in the floor, you may have to overpressurize parts of your floor so that the low pressure areas get enough air coming out of them. We commonly see plenum pressures in the kind of, I would say 2 to 3.5 inches, or 0.02 to 0.035 range when measured in inches of water. But I've been in data centers, as Rob just mentioned, where they're well over 0.05, and you're rattling ceiling tiles in the room. So the lower you can get it and still safely operate, the better.
And Tim, I know you'll have an answer for this one. Are directional floor panels really effective?
Yeah, they really are. I've seen head-to-head competition between directional floor panels and kind of a quote-unquote standard high high flow airflow panel. And you have to take some things into account, like the direction of the airflow under the floor. But by manipulating the orientation of a directional airflow panel, you can definitely increase the amount of air that is directed at the front of the rack versus bypassing the rack. We've seen head-to-head where temperatures with a directional panel drop much faster and much lower than when up against a different type of airflow panel.
Do you guys have a view on air handler fans under the floor versus above the floor?
I'm not sure I fully understand the question, but if we're talking about like a perimeter room air conditioner and kind of how its fans are set up, usually if it's a pressurized raised floor, you know, the fans and they're today, you know, it's the EC plug fans are the most energy efficient and are typically included with a manufacturer's unit. There are certainly upgrades available if you've got kind of the old squirrel cage fans, but typically they drop under the raised floor and that's where they deliver the air from. If they're, you know, you can have that same perimeter unit blowing air out above the raised floor, and that's how cooling's delivered. It's a little bit more challenging from a containment standpoint and certainly to control the mixing because you've got both the supply and the return coming in kind of above the raised floor. But typically on a perimeter raised floor with a pressurized or perimeter crack units with a pressurized raised floor, the fans are underneath the floor in a frame that's underneath the unit. I don't know if that helped answer it or not.
I hope so. In your experience using hot aisle versus cold aisle containment, is there a preference and is there an efficiency difference between the two?
I'll start. I'm sure Tim will chime in. So we've both said this throughout this presentation. We said it in previous ones that data centers operate very differently. Even ones with pressurized raised floor and cold aisle containment, one can be very different in how to set it up and manage it. But I'll start with the hot aisle containment. Newer deployments with higher densities, if you can do hot aisle containment, I would suggest it. So there are some prerequisites that require it. You've got to have hopefully either really tall ceiling or above your ceiling is a full return air plenum that you can take advantage of. So with hot aisle containment, you know, your barriers go from the top of the rack up to the ceiling, and then you've got a lot of the kind of egg crate. Instead of solid tiles in the ceiling in that hot aisle, it's full of egg crates, and you're using the fans in your perimeter units to pull that hot air up and return it directly. So there's no mixing of the supply air. Now your room is fed with cold air, right? You've got cold air going to your cold aisles. You got cold air going into the rest of the space. So you can effectively raise your set. We've been in hot aisle containment where the room's, you know, 75 degrees. And the hot aisles are, you know, in the upper 90s. If you can do that, I've seen data centers operate at higher densities and racks and manage it more effectively. It's also easier to do if you have a slab floor and you don't have a raised floor, but that's a different discussion than, you know, we were featuring today. Cold aisle containment, for whatever reason, I see as being more popular for companies that have pressurized raised floors. But now you're, you know, supplying cold air just to the cold aisle. You're not putting perf tiles in the hot aisles so that now your room's a little bit warmer because it's kind of one big hot aisle instead of a contained cold aisle. So I've seen higher densities managed better and more effectively with hot aisle containment, but that doesn't say cold aisle containment. It's not effective. We see it implemented a lot more.
I would second that. I think where we see hot aisle containment being implemented is in brand new build outs, where if you're in an existing data center, or maybe a slightly older data center, the option is typically cold aisle containment. The only other thing I'd mention about hot aisle is I think you probably could get a slight efficiency gain if you did a kind of equal comparison between two rooms that were the same, hot aisle versus cold aisle. But you have to remember that those hot aisles can get, like you said, in the high 90s or even above that. And from a working environment standpoint, there are a lot of customers who just don't want their people working in the hot aisle when they're that hot. So.
Next question we have for you guys. If floor perforated raised panels are used, should we add a nozzle for fire suppression under the raised floor?
Well, I'm not a fire suppression expert, but typically the plenum space is considered, from a fire containment standpoint, fire monitored space already. If you're blowing air into the plenum, you're going to have fire suppression systems in your data center that are equipped to deal with that. So typically, just adding additional raised floor or airflow panels in the space does not require that you do anything different with your fire suppression system. You do have to be careful when you move to containment, because a contained space can be considered another plenum, which may require either its own separate fire suppression system, or the containment must be installed in a way that if there is a fire, the ceiling of the containment or the walls of the containment either kind of melt or drop away, so the existing fire suppression system can accommodate any fire that would potentially happen in that contained space. But just adding perforated panels to an existing raised floor that was designed as a data center would not require additional fire suppression.
One more question here. What is an acceptable leakage through a standard raised floor without any racks and cutouts?
Again, that's going to be a little bit different. It's going to depend on the floor pressure. What we've seen and what I think is typically used when you're setting up like a CFD model, and Rob, you can correct me if I'm wrong, but is about 1.5%. And that assumes, a very level floor and all panels fitting together neatly and nicely. The more plenum pressure you have, though, the more leakage you have through that floor. But that's kind of typically what the assumption is, I believe, around 1.5% through a raised floor.
That's what I've been reading and what I've heard as well, Tim.
All right, excellent. I think we've worked our way through the questions that were submitted through the chat, and we are also a little bit past our time limit. So in conclusion, I'd really like to thank you all for spending your morning with us this morning. We appreciate having you here. We appreciate your interest in this topic. All your questions in the live chat and the conversations that have been going on there are really great. If you have questions after the webinar ends, you can either contact Rob or Tim or both of them. Their information is there on the screen. You can email Rob at info@criticaleg.com. You can get to Tim at sales@rletech.com, or you can reach out to both of our companies through our websites. This recording will be archived. It will be available for you guys after we get it uploaded to our websites, and you will all receive an email at the end of the presentation once the webinar is uploaded with a link for you to view and share the webinar. And we've also had some interest from questions here about the other 3 webinars in this series, so we'll make sure that you are all provided with links to access those as well. So unless there are any other questions, unless Tim and Rob, you have anything else you need to add this morning?
Nope, just thanks to everybody again, and hope you and your families and coworkers remain safe. Appreciate you attending.
Yep, thank you very much.
Absolutely. Thank you, everyone. Have a great day. We appreciate hearing from you this morning.